students, welcome to Sunil's tutorial. I'm Sunil Midwani and today we'll be doing this chapter called as wave motion. Let's move on ahead. Let's see how does the phase change take place. Let's see the change in phase. Right? Now we try to see reflection of sound. Right? Now what happens when there is reflection of a transverse wave? Reflection of transverse wave. Now in the case of reflection of a transverse wave, if you have incidence, for example, let's assume that this is my barrier, this is the incident wave, this strikes here. Now in this case, when the transverse wave is reflected from a denser medium, the medium from where it is going to be reflected, then the velocity is reversed and there is a phase change of 180 degrees. So my reflected wave would be like this. This is incident wave and this is reflected wave. And the other thing is, so I can say that when transverse waves are reflected, at the surface of the denser medium, the particle velocity is reversed. And a phase change of pi radians is produced. Right? So in this case, a crest is reflected as a trough and a trough is reflected as a crest. So this is how you would have reflection of a sound from a denser medium. Now let's try to see reflection of a sound from a rarer medium. Suppose if I have a rarer medium, let's draw this as a rarer medium. This is my incident ray. In the case of reflection of sound from an incident ray, there is going to be no phase change. The sound is going to be reflected in the same phase. This is my incident ray, incident wave. This is reflected wave, right? And this is your rarer medium. The previous case, this was the denser medium, right? So I can say that there is no change in phase. There is no change in phase during reflection at a surface of rarer medium. Right? The velocity is not reversed and there is no change in phase. There is no change in phase during the reflection at the surface of a rarer medium, and the velocity is not reversed. So that is how a transverse wave would be reflected, right? Now let us see the reflection of a longitudinal wave. Reflection of longitudinal wave. let's see reflection of a longitudinal wave. Now incident as a rarer medium to a denser medium, right? The reflection produces a phase change of pi radians and there is a reversal of velocity, right? Thus a compression gets reflected as a rarefaction and a rarefaction gets reflected as a compression, right? I can say that when longitudinal wave are reflected at the surface of denser mediums, the particle velocity is reversed. The particle velocity is reversed and a phase change of pi radians is produced. So it's same for longitudinal and transverse waves. How do we get this? Same way, when a longitudinal wave, I can say when longitudinal waves are reflected at the surface of rarer medium, and longitudinal waves are reflected at the surface of a rarer medium, the particle velocity remains same and no phase change occurs. So it is the same for longitudinal as well as transverse wave. Next, let's understand what is superposition of waves. What do we understand by superposition of waves? Right? When two waves traveling through a medium arrive at a point in the medium simultaneously, then each wave produces its own displacement at that point independent of the other. Hence, the resultant displacement that is produced is equal to the vector sum of the individual displacements produced by the wave. I have one wave that is going to travel through air and reach this point. I have another wave that is going to travel through air and reach this point. This wave will produce some displacement, this wave will also produce some displacement. The net displacement produced at this point will be the vector sum of the displacement produced by the two waves. That is called as principle of superposition of wave. So I can say that principle of superposition of waves states that when two waves traveling through a medium simultaneously arrive at a point simultaneously, each wave produces its own displacement at that point. Each wave produces its own displacement at that point independently of the other. each wave produces a displacement at that point which is independent of the other. Hence the resultant displacement at that point is equal to the vector sum of the individual displacement of all the waves. Vector sum of the individual displacement of all the waves. Displacement of all the waves. Right? That's your principle of superposition. So if two waves reach at a point simultaneously, the net resultant will be the vector sum of the two waves. Right? Now, what are the important points to be considered in case of superposition? Important cases of superposition. The important cases that have to be considered while you are going in for superposition of waves is that the two waves of same frequency moving in same direction will result into interference of waves. The two waves of slightly different frequency moving in the same direction will result in the phenomena of beats. Two waves of the same amplitude and same frequency but moving in opposite direction will result in stationary waves. So it is through principle of superposition of waves that all the three phenomena are obtained. Right? Either I can get interference of waves, or I can get beats, or I can get stationary waves. Right? How are all these three produced? All the three are produced by using principle of superposition of waves. So I can say if two waves of same frequency, this gives you your definition for all the three different types of waves that can be produced. Two waves of the same frequency moving in the same direction, result into interference of wave. So how do you get interference of wave? You get interference of wave when you have the two waves moving together in the same direction with the same frequency. Right? You get this? The two waves will join each other using superposition, and that will result in interference of wave. Right? Next, the two waves, if two waves of slightly different frequency moving in the same direction result into phenomena of beats. So if the two waves have slightly different frequency and are arriving at a point simultaneously, what you would get is beat frequency, where at a certain point you will hear a very high sound, at a certain point you will hear a very low sound. We'll go into beats in detail. And third, the two waves of same amplitude and same frequency, if two waves of same amplitude and same frequency moving in opposite direction form stationary waves. So you can have three different types of superposition. Either superposition would lead to interference of wave or beats, or it would lead to stationary waves. Right? Now when superposition of waves takes place, what are the different ways it can take place? Right? When the two waves are arriving at a point simultaneously in the medium, then the resultant displacement is going to be the vector sum of the displacement of the individual waves. Now this modification in displacement would result in superposition. Here you could have two effects. Either you would have a displacement that would be the addition of the two, or you would have a displacement that would be the difference between the two. This gives rise to two different types of displacement which are called as constructive and destructive interference. Right? Do we get this thing clear? So you can have constructive and destructive interference. I can say that what is constructive interference? If the waves arrive at a given point in phase, right, then the crest of one will coincide with the crest of the other, and similarly the trough of one will coincide with the trough of other. Similarly, if it is a longitudinal wave, the compressions will coincide and the rarefactions will also coincide. As a result, the resultant amplitude will be maximum. That will be twice the amplitude if the two amplitudes are same, and this kind of interference would be called as constructive interference. Right? So I can say that if two waves arrive in phase, if the two waves arrive in phase, the resultant amplitude at the point is maximum. Right? That is twice the amplitude of the either wave, and this type of, that is maximum, this type of interference is constructive interference. Right? Then you have destructive interference. Right? If the two waves that arrive at a point are 180 degree or 5 radians out of phase, then the crest of one will coincide with the trough of other, right? Or the compressions will coincide with rarefactions. Therefore, the resultant amplitude will be minimum, and that is called as destructive interference. Right? Do we get this thing here? If the two waves arrive 180 degree or 5 radians out of phase, then the resultant amplitude at the point is minimum. This type of interference is destructive interference. So you can have constructive interference and you can have destructive interference. Next, let's move to beats. I already defined what was interference. Now I also defined what are beats. Two waves of slightly different frequencies moving in the same direction and interfering with each other. Now what are beats? How do I actually define beats? That's how beats are formed. Beats are nothing but the periodic rise and fall in the resultant intensity of the sound. If the resultant intensity, if there is a periodic rise and fall in the resultant intensity of sound caused by superposition of waves, then that is called as beats. Either you will hear a very high frequency or a very high sound, or you will hear a very muffled kind of a sound, right? So that is called as, that phenomena is called as beats. So how do I define beats? It is the periodic rise and fall in the resultant amplitude rise and fall in the resultant amplitude or resultant amplitude of sound caused by superposition of two sound waves. Superposition of two sound waves. Superposition of two sound waves having slightly different frequencies. Having slightly different frequencies traveling along the same line in the same direction. Traveling along the same line in the same direction. That is what is beats, right? That's called as the phenomena of beats. Now I said it is a periodic rise and fall in sound, right? Now when maximum sound is heard, there is a periodic rise in the intensity of sound. That is called as waxing sound. When there is a fall in sound, when you have a muffled kind of a sound heard, then that's called as waning sound. So beats result in the formation of waxing and waning sound. When you hear maximum intensity, that is called as waxing sound. When you hear minimum intensity, that is called as waning sound, right? So the phenomena of beats produces loud and faint sound at regular interval, right? The loud sound is called as waxing. The maximum of the loud sound, the maximum of sound is called waxing, and the minimum sound is called waning, right? So what is one beat? One beat is one waxing and one waning combined together to form one beat. Therefore I can say that beat is one waxing and one waning, right? So one waxing and one waning form one beat. And we get this in that case, what is period of beat? Period of beat. The time interval between two successive waxing and two successive wanings is called as the period of beats. Time interval between two successive waxing or waning is called period of beats. Finally, we get this in here. Next, what is frequency of beats? frequency of beats. The number of beats heard per second is called as frequency of beats. Number of beats per second is called frequency of beats. So that's my introduction to beats. It's nothing but the periodic rise and fall in sound caused by superposition of waves. Right? Now, let us derive an expression for beats. Expression for frequency of beats. Let's derive an expression for frequency of beats. Now, let's consider that there are two sound waves of the same amplitude and slightly different frequencies traveling in the same direction along the same line. So consider two sound waves of amplitude A. Consider two sound waves of amplitude A and frequencies N1 and N2. Let's assume that N1 and N2 are the frequency such that N1 minus N2 is very small. Right? Now, let the two waves arrive in phase at a point. Let the two waves arrive in phase at a point. Right? Let us consider that y1 and y2 are the displacement of the particle at that point. Let y1 and y2 be the displacement. Let y1 and y2 be the displacement of the particles at that point at time t due to the two waves. Right? I can say therefore y is equal to a sine 2 pi n1t and y2 is equal to a sine 2 pi n2t. Now I would say that by principle of superposition, y is equal to y1 plus y2, therefore y is equal to a sine 2 pi n1t plus a sine 2 pi n2t. Y is equal to a common sine 2 pi n1t plus sine 2 pi n2t. Right? Sine plus sine is 2 sine cos. So I'll get y is equal to a 2 sine 2 pi n1t plus 2 pi n2t upon 2 cos 2 pi n1t minus 2 pi n2t upon 2. So this can be written as y is equal to 2a sine 2 pi t common n1 plus n2 upon 2 cos 2 pi t common n1 minus n2 upon 2. Right? Now, once I have this, I can say that let us assume, I can just rearrange this, I can say y is equal to 2a cos, I am rearranging, 2 pi n1 minus n2 upon 2t into sine 2 pi n1 plus n2 upon 2t. Now, let us assume that let 2a cos 2 pi n1 plus n1 minus n2 upon 2 into t be equal to a. Let us assume that that is equal to amplitude, and let us assume let n1 plus n2 upon 2 be equal to capital N, in which case my equation will turn to y is equal to a sine 2 pi nt. That means the resultant, and this is the equation of a sine wave, hence I can say that the resultant wave is also a simple harmonic wave, which is the equation of an SHM. Hence I can say that the resultant wave is also an SHM. Right? So we now know that the resultant wave is an SHM. Now I can say that where the amplitude is going to vary with time, I can say that where, consider, we have said that A is equal to 2A cos 2 pi n1 minus n2 upon 2t. So I would say that the amplitude is directly proportional the amplitude of the resultant motion is not constant, but it is going to vary with time. And I could also say that the frequency component of the sound, that is going to be n1 plus n2 upon 2. It has got an amplitude component, it has got a frequency component. The frequency component of the sound is nothing but the arithmetic mean of the two frequencies. The frequency at which the beats are going to be produced is going to be the arithmetic mean of the two frequencies. Right? Now, we already know that intensity of sound is directly proportional to square of amplitude. Intensity of sound is directly proportional to square of amplitude. Now, the resultant intensity of sound will be maximum when the amplitude is maximum. You can say that resultant intensity of sound will be maximum when amplitude is maximum. Now guys, A is equal to 2A cos 2 pi n1 minus n2 by 2t. There is a cos function. The maximum and minimum value of cos function are 1 and 0. Therefore, I can say that the maximum amplitude, if I consider the cos function, the maximum value of cos function is plus minus 1. So the max amplitude will be plus minus 2a. That will be the maximum amplitude which is possible when the value of cos function becomes plus minus 1, when cos 2 pi n1 minus n2 upon 2 into t becomes equal to plus minus 1. Now, we know that cos of 0 is 1. Cos function will become 1 when the angle is 0 or the angle is 180 or it keeps varying by 180, right? Which is possible when pi n1 minus n2 upon 2 into t becomes equal to 0 or pi or 2 pi or so on, right? Now if this is the value, I can say that, therefore I can say that if t is either t has to be equal to 0, which is possible then for this answer to come to 0, which is possible, the only variable parameter there is t, which is possible when t should be equal to 0. When t is 0, I get the answer as 0. Now I want the answer as pi. That means what should be the value of t? The value of t should be nothing but 1 upon n1 minus n2. Guys, in this equation, if the value of T is 1 upon N1 minus N2, N1 minus N2 will cancel, 2 and 2 will cancel, I'll get my value pi. Or it should be equal to 2 upon N1 minus N2 and so on. So the time period between two successive maxima, therefore I can say that the time period by maxima, because I'm considered maximum amplitude, the time period between two successive maxima is going to be 1 upon N1 minus N2 minus 0, so which will be equal to 1 upon N1 minus N2. That is going to be my time period between two successive maxima, right? Now we know that frequency is nothing but 1 upon time period, right? I can say therefore frequency of beats, frequency of beats is nothing but 1 upon time period. So this is going to be frequency is going to be 1 upon N1 minus N2, or frequency is F here. So frequency of the beats is going to be N1 minus N2. So that is going to be my frequency of the beats, right? This is when I have maxima. What if I have minima, right? Let's check this if it is minima. Now I can say that A is equal to also A is equal to 2A cos 2 pi N1 minus N2 upon 2 into T, right? Now minimum amplitude, what will be the minimum amplitude that I can obtain? The minimum amplitude that I could obtain would be 0. That is the minimum amplitude that I can obtain. Now minimum amplitude can be obtained, which is possible when see, A cannot be 0, so it's the cos function that will have to be 0 to get an amplitude of 0, which is possible when cos 2 pi N1 minus N2 upon 2 into T becomes equal to 0. But cos function is 0 when the value of the angle is 90 or 270 and so on. I can say which is possible when pi N1 minus N2 upon 2 into T is either 90, cos of 90 is 0, or 270, 3 pi by 2 and so on, right? Now I can say which is possible now here 2 pi N1 and N2 will not change, the only value that will change is T. Now if I want a pi by 2 in the answer, then it should be equal to, I need to have N1 minus N2 in the denominator, that will cancel, and I need to have 2 in the denominator. So if I have 2 in the denominator, this 2 and this 2 will get cancelled, N1 minus N2 will get cancelled, so that will give you 1 upon 2 N1 minus N2. Fine, do you get this thing here? Similarly, if I want 3 pi by 2, this will give me pi by 2. I want 3 times, so this should be 3 times twice N1 minus N2 and so on, right? Therefore, the time period between two successive minima, therefore, the time period between two successive minima is going to be equal to 3 upon 2 N1 minus N2 minus 1 upon 2 N1 minus N2, right, which is going to be equal to common denominator 2 N1 minus N2, 3 minus 1 2, this and this gets cancelled, so time period between two successive minima is going to be 1 upon N1 minus N2, but frequency is nothing but reciprocal of time period. Frequency of beats is nothing but 1 upon time period. So the frequency of minima is going to be 1 upon n1 minus n2, that is n1 minus n2. Right? So the frequency of minima, that's the waning period, will also be equal to 1 upon n1 minus n2. Fine, do we get this thing here? Okay. Next. So do we understand what is beats? Next, let's try to understand something else. Let's try to understand what is Doppler effect. We've done beats. Next, Doppler effect. Let's try to understand what is Doppler effect. Now, when you are standing on a railway station, as the train approaches the station with a whistle and leaves the station, the frequency or the sound of the whistle that you hear when the train is far away, when it reaches the station and leaves the station, is different. Right? What happens is that if either the source or the object is moving, then the frequency that the observer will hear will be different than the original frequency. Right? And this is called as the apparent frequency that he will hear is called as the Doppler effect. Right? It is, why is the Doppler effect caused? It is the apparent change in the frequency caused due to the relative motion between the source and the observer. If either the source or the observer or both of them are moving, then the frequency with which you will hear sound will be different than the frequency with which it is spoken, and that is called as Doppler effect. Right? So what is Doppler effect? It is the apparent change in the frequency, of the sound due to the relative motion between the source and the observer. The apparent change in the frequency of sound due to the relative motion between the source and observer is called Doppler effect. Right? Now, why does this happen? Let's try to understand the phenomena of Doppler effect. Let us consider that I have source here, the object is situated here. Let us consider longitudinal waves. The waves are equally spaced. This is the distance between two consecutive refractions, right? Which is going to be my lambda. Now let us assume, so in that case, v, let us assume, is the velocity with which the sound is going to move from the source to the observer. Fine. Now let us assume that the source moves. If the source moves, let us assume that the source comes here, the observer remaining fixed. The source has reached this point, the observer is here. So as a result, what will happen is, if he is speaking with the same frequency, the distance between the two successive compressions and refractions will reduce, right? So what you see is that there is going to be a change in the wavelength. There is a change in the wavelength. Moreover, if the source has moved from its original position to new position with a velocity of say Vs, then from the source to the object, the velocity is going to be V minus Vs. The total velocity was V, out of which the source has already covered a distance with a velocity of say Vs. Let's call this wavelength as say lambda 1. Right? So as a result, he is not going to hear since the velocity changes and the wavelength changes, automatically frequency will change. V is equal to n lambda. Lambda is also changing, V is also going to change, right? So as a result of this, the frequency with which I will hear the sound, it is not that the frequency with which the source is speaking is going to change. The frequency with which the sound will be heard by you will be changed, and this apparent change in the frequency is called as Doppler effect. Yeah, you wanted to ask me something?
What Vs?
Vs is the velocity with which the source is moving. Fine, do we get this thing here? So, do we understand the basic concept of Doppler effect? Let's write this down, guys. Why Doppler effect takes place? I can say that let S be equal to the source of sound and O equal to observer. Right? Let us assume that S is the source of sound and O is the observer at rest at a distance of say V. The distance between the source and the observer, right, at a distance of V from each other in the beginning, right. Let us assume that V is also the velocity of sound, right. Let us assume N is the frequency of the source, true frequency of the source, true frequency of source, right. In that case, now as the source is stationary, the number of waves reaching the observer per second is going to be n, as or when the source is stationary, the number of waves reaching the observer per second is say n. Let's assume those are the number of waves. Now let us consider a case where the source starts moving towards the observer, right? Let's assume that the source moves towards the observer with a velocity of Vs. Let source move towards the observer with a velocity of say Vs. Vs is the velocity with which he is moving, right? Now in that case, the source emits the first wave at an instant it starts moving from the position that it was, right? Now since the distance is covered in 1 second, therefore I can say that the distance is going to be equal to Vs. Let us assume that he covers that distance in 1 second, right? As he moves from one position to another position, he covers the distance in 1 second. So I can say that the source emits the first wave. Source emits the first wave. The source emits the first wave and moves through Vs to reach a new position and moves through Vs to reach a new position, right? Now in that case I can say that counting the first wave emitted by the source at the original position to the time when he reaches the new position, you will see that the number of waves that would reach would change, right? The number of waves by the time he moves from here to here, you would have certain number of waves reaching the, if he is speaking with a frequency, you would have certain number of waves that will reach the observer. But if the source moves from one position to a closer position, then you would have more number of waves reaching the observer, right? So I can therefore say that if n number of waves were emitted by the source, if n waves were emitted by the source, if n waves were emitted by the source during the 1 second, then during the 1 second at the original position, when he reaches the new position, these waves are crowded. These waves get crowded, right? These waves get crowded because the distance between the source and the observer decreases due to the decrease in the distance between source and observer, right? So in which case now the waves have to cover a distance of, so initially they were covering a distance of v. Remember, we are considering time as 1 second, therefore velocity and distance is the same, right? Initially they were covering a distance of v. The source has already covered a distance of vs, so now the sound waves have to cover a distance of v minus vs. Those many waves are going to be now crowded in that much space, right? Crowded due to the decrease in the distance between the source and the observer. The waves have to cover a distance v minus vs, that is the distance that the waves will have to cover. Therefore the wavelength will decrease. Therefore wavelength, since there are more waves crowded in the same space, the wavelength changes. Wavelength decreases, right? Wavelength decreases to, say, let us assume lambda 1. Let's assume lambda 1 is the new wavelength, right? So in other words, since the source is emitting each successive wave as he is moving towards the observer, the waves emitted from the source cover a smaller and smaller distance to reach the observer, right? Since the velocity and the velocity of the distance is changing and the wavelength is also changing, therefore the apparent frequency with which the observer will hear this will also change. Let us assume that the frequency heard by the frequency of sound heard by the observer is, say, n bar, right? Now I can say where n bar is the apparent frequency. So in which case I can say that the apparent frequency that the observer will hear was v upon v minus vs times the original frequency. Fine? Do we get this thing here? So thus, if the source is moving towards the observer, this is the apparent frequency with which the observer, or this is the apparent frequency that the observer will hear the sound with, which will be original velocity upon change in velocity into the original frequency. Fine? Okay. We'll stop this here for the day. Thank you very much.